So, good afternoon, everyone. My name is Subhadeep Basu. I'm from TCS Research Kolkata. On behalf of my all the co-authors, today I would like to present our paper entitled Signal Energy-Based Probabilistic Inspection of Defects in Composites. So, let's begin. Now, before jumping into the main discussion, I would like to quickly tell about the basic aim or motivation behind this study. So, the basic aim or motivation for this study is to produce a baseline-free damage detection technique based on signal energy using ultrasonic guided wave testing. This method is particularly useful for highly attenuating composite materials. We all know that composite materials are nowadays widely used in different sectors. For example, aerospace, automobile, wind turbine blades, etc., and so on, for its superior strength and durability. So this method can be useful in that domain also. So here we are basically proposing a preliminary work. Now, in the context of damage localization in the composite material, there are various techniques that have been used or explored over the years. One of the technique is basically guided wave ultrasonic testing. So this has been explored over the years and over past 2 decades drastically. And in guided wave ultrasonics, we basically use two algorithms, namely one is the rapid and another one is the nonlinear rapid. So rapid is basically stands for reconstruction algorithm for probabilistic inspection of defects. So what this algorithm does is, this algorithm has two parts, as it is shown by equation number 1. So this first part basically computes the AIJ or signal dissimilarity coefficient. So this basically calculates the signal dissimilarity coefficient based upon the correlation between baseline samples and baseline sheet and the sample sheet. And the second part, that basically beta minus R divided by beta minus 1, that basically computes the damage trajectory using triangulation method. So there are few certain limitations with the current existing SOA techniques. First of all, that rapid always requires one baseline data or one ground truth data to be available. Then only we can do the damage localization or defect localization in any of the materials. And secondly, in case of nonlinear rapid, so it always requires two different types of voltage to be excited. One is for high and another one is low voltage. So what happens is, when we have a very high attenuating composites, getting good response at the receiver for low input signal is very challenging. So our work basically tries to overcome these certain limitations. So this is basically the working principle that we are proposing. So first, we are basically determining the velocity of ultrasonic wave in any kind of material using one transceiver system using pitch catch method. So what we are doing is, we are basically placing one transmitter and one receiver at a fixed distance, and we are basically transmitting ultrasonic tone burst of a fixed frequency, a fixed number of cycle, and fixed amplitude through the transmitter. And it basically, its response is captured by the receiver at the other end. Now, while we are capturing the response at the receiver at the other end, we are basically examining the first highest peak to calculate its velocity. So velocity calculation is quite straightforward. So we have a certain fixed distance, and we observe the first peak where we are getting the signal at the receiver end. So if we divide the d with respect to the time, so we will obtain the velocity. Now, what we are doing is, we are basically selecting a time window around that first peak of arrival. So this basically time window duration is, we are selecting from t minus delta t by 2 to t plus delta t by 2. So this is the duration of time window. It's around delta t. Now what we are doing is, we are basically introducing a term called energy ratio. So what it does is, we are basically calculating the energy of the transmitted signal. Two, we are calculating the energy of the windowed received signal. One thing to note here is that the energy of the transmitted signal remains same, because we are basically transmitting the same signal for different purposes. And in general, what we do is, for any defect localization, we generally use multiple transmitter and multiple receivers for proper localization of damage. So if there is some sort of damage or defect present in the structure, then the energy of the windowed received signal, that is basically U1, that will change. And depending upon that that factor, that energy ratio EIJ for that path will also change. From that, we can estimate where the damage is or where the defect is. Now, one thing we have to bear in mind that energy can be reduced when there is a defect in the path or defect in the material, as well as when the signal propagates through any attenuating medium or any composite medium, its energy also decreases. So we have studied the literature and we have observed that its amplitude basically is inversely proportional to the square root of the distance. So here what we are doing is, so we are basically we are scaling the signal energy ratio by a factor of the distance d. Distance d is basically the distance by which the signal is basically the path it has traveled. So with this scaled energy ratio term, we are introducing, and this basically corresponds to our governing equation 2, where in EIJ we are incorporating in that equation, and the remaining part remains the same. So after that, we are basically predicting the damage location, and we are basically calculating its centroid by method of moments. It's a kind of standard technique. And to check how close the predicted damage is from the actual damage, we are basically calculating the absolute error between these two. That is basically the center of the actual damage to the centroid of the predicted damage. So here is the experimental setup that we have used. So we are using glass fiber epoxy based composite sheets. Generally, these are commercially available as FR4 substrate. These FR4 sheets are generally used in PCB board, printed circuit board, or in any substrate of the microstrip patch antenna. In that case, we are basically using FR4 sheets. And the dimension of a FR4 sheet is 460 mm cross 310 mm cross 2 mm. The thickness of the sheet is 2 mm. And we are creating a defect by scratching a spot at the backside, and we are basically attaching a coin to mimic some sort of manufacturing defect. So the defect is at the backside. It is completely optically occluded, meaning you cannot observe any kind of defect from the top of it. By just looking at it, you cannot see any kind of defect. Now, regarding data collection, we are here using various multiple number of sensors. We have placed 8 ultrasonic sensors. These are attached in these FR4 sheets. And we are inspecting an area of 200 mm cross 200 mm. So we are basically covering the entire inspection area. And here we are doing a data collection by tomographic approach. So what I mean by tomographic approach is that when one sensor is basically transmitting, its response is captured by all the other sensors. And this is basically done for all the other sensors, meaning the next sensors then starts, and its response is also basically captured by all the other receivers. So by that, we have a kind of total good number of database of all the received signals. And we have done this work for 2 different sensor array locations. And regarding input signal characteristics, we have used like Gaussian modulated tone burst. And voltage, we are kind of exciting input voltage is around 130 volt peak to peak. We are using 5-cycle tone burst with a frequency, center frequency at 389 kilohertz, because the piezo has a resonance peak of 389 kilohertz. However, in other frequencies also, we have also tested and we have also carried out. For sampling, we are sampling it at 40 megahertz sampling frequency, and the duration for each received signal for each path is around 205 microseconds. And total number of paths that we are considering in this experimental system is 28. So here is basically the results that we are doing. So in figure 3a, so here you can see the actual defect is basically in somewhat in the middle or in the center. It is shown in the white circle, and the inspection area is basically shown using white dotted lines. So that red region is basically indicates that predicted damage area with high probability values, and this is also shown using the color map plot. We have found out that the actual defect location is at 280 mm and 180 mm, where the predicted defect centroid is around 281 mm and 184 mm. So we have an error between the actual and predicted one is coming out to be around 4.12 millimeters. And in the next case, so in figure 3b, where we have damage in non-line of sight position. So it is not in the middle, it is somewhat at the right side upper corner. You can see the predicted defect area is basically shown using black dotted circle, while the actual defect is basically shown using the white circle. And here also we can observe that predicted defect centroid at 275 mm and 195.3 mm, while the error between the actual and predicted defect position is around 16 mm. So this is for time window when we are selecting time window of 20 microseconds. Next, we have also varied the time window for 20 to 40 microseconds. So these are the results of damage localization for 40 microseconds. So here we can observe that in case of when the damage is at basically line of sight position, the error between the actual and predicted damage is remains more or less same. But at the figure 4b, basically it depicts when there is damage in the non-line of sight positions. So the error between the actual and predicted damage is very close. It is also around 16.28 mm compared to the 16.15 mm, the previous window. And this is basically the last time window that we have presented here. So this is for defect localization using 60 microsecond time window. Here we have done for both the cases, meaning when the defect is at line of sight position and also when the defect is at non-line of sight positions. So this table basically shows the comparative analysis of defect localization with all three different time windows that we have shared, we have considered, and for two different sensor array locations that we have considered, sensor array location 1 and 2, and its absolute error is also indicated in this table. So the takeaway is this basically this algorithm or this approach is kind of easy to implement, and this is a baseline free inspection for defects utilizing the scaled signal energy. And the third point, which is, and it is not much immune to the duration of the U. Now, as a future scope, we would like to improve the accuracy of the damage detection, as well as we'd like to explore this technique to various different types of composite materials and different types of damages. So these are the references that I have used for this study. Thank you very much.